In the vast silence of space, even the smallest change can rewrite everything we think we know. 2 nights ago, something happened that sent shockwaves through every major observatory on Earth. The interstellar object known as 3.I/ATLAS suddenly brightened, not gradually, but explosively. The iridescent haze of a stranger from beyond our solar neighborhood has just revealed something extraordinary. The James Webb Space Telescope, JWST, has confirmed that the interstellar visitor, 3I/ATLAS, is exhibiting behavior and composition unlike anything seen before in our solar system. This fleeting wanderer hurtling through our realm of planets and asteroids is rewriting our understanding of how interstellar objects evolve, what they carry, and perhaps how many secrets the broader galaxy has imposed upon them over billions of years. Discovered on July 1, 2025 by the Atlas Survey in Chile, 3I/ATLAS immediately drew attention as the third confirmed interstellar object to traverse our solar system, following 1I/Oumuamua and 2I/Borisov. But what JWST's infrared eyes have revealed goes far deeper than mere novelty. The comet carries with it a chemical fingerprint and physical history that indicate long-standing exposure to galactic radiation and an icy core whose outer layers have been radically transformed by wandering the Milky Way for eons. According to the science, these outer layers form a 15 to 20 meter crust rich in carbon dioxide gas that has been converted from carbon monoxide by cosmic rays. It is the kind of revelation that shakes up long-held presumptions. We have treated comets and small bodies from other star systems as time capsules, pristine relics, carrying the chemistry of their birthplaces. But 3I/Atlas seems less like a clear window into another star's protoplanetary disk, and more like a battered traveler, its surface forever altered by a relentless barrage of high-energy particles. The spectroscopy performed by JWST's near-infrared spectrograph, NIRSPEC, on August 6th, showed CO2/H2O ratios of around 8 ± 1, one of the highest ever measured in any comet-like object. At the same time, water vapor appears relatively suppressed compared to expectations for solar system comets. The coma is dominated by CO2, an anomaly that demands a rethink of the narrative of interstellar comets. Because of this, there is a profound implication. If interstellar objects spend tremendous time wandering the galaxy, exposed to cosmic rays unshielded by a sun's heliosphere, then what we observe in them may no longer reflect formation chemistry, but rather a long and slow remodeling process. 3/ATLAS is now being described as a paradigm shift. The outer visible layers of its nucleus, rather than being pristine, appear to have been significantly processed by galactic cosmic radiation, altering ices, converting molecules, and even structurally reworking dust and ice mixtures. In short, this is an object that tells us more about the voyage across billions of years of space than about the birthplace of the comet itself. As the object now barrels inward, approaching perihelion at about 1.36 astronomical units on October 29, 2025, JWST observations capture a moment in its evolution. The heat of the sun will begin to erode this irradiated crust and expose deeper layers. But even the outgassing we detect, currently dominated by CO2, suggests that the outermost 15 to 20 meters of crust may be what we are primarily seeing. According to scientists, this irradiated zone has effectively separated the observable properties of 3I/ATLAS from its underlying primordial composition. The result? The comet we perceive is more of a cosmic survivor of Milky Way harshness than a freshly preserved baby of another sun. This new finding raises major questions about how we classify interstellar objects, and how we might interpret their chemical signatures. If an object spends billions of years in interstellar space with relentless exposure to high-energy particles, then the assumption that their surface layers reflect initial formation conditions may be flawed. In fact, we might never be able to peek into their unaltered interior without deep penetration or fortuitous disruption. The thick, irradiated crust observed on 3I/ATLAS suggests that what we see is the processed outcome of its journey, not the original blueprint. From a chemical and physical evolution standpoint, this means that the abundance of CO2 relative to H2O in 3.I/ATLAS may not primarily reflect where the comet formed, but rather how it has been processed over time. Laboratory experiments indicate that galactic cosmic rays convert CO2 into CO2 efficiently over long timescales, and then form organic-rich crusts at the top of icy interiors. The steepening of the spectral slope of 3.I/ATLAS's coma, the unusually high CO2/H2O ratio, and the overall outgassing properties all align with this processing model. Consequently, the comet's current state is like a geological record, not of its birth environment, but of its eons-long interstellar exile. Another striking implication is that our models of volatile retention, thermal processing, and outgassing in interstellar objects must be revised. Traditional solar system comet models reasonably assume that water sublimation dominates as the object approaches the sun, because H2O is abundant and more available. But 3I/ATLAS has upended that notion. Its water activity is relatively low, yet it's active well beyond the distance where water sublimation usually dominates. Observations from the Swift Ultraviolet Optical Telescope detected OH emission at 3.51 astronomical units, suggesting water release at distances where water ice typically is dormant in solar system comets. That means the comet's activity machinery and volatile budget has been altered, rewired by its exposure history. For instance, if the outer layers are hardened or insulated by a radiation-induced crust, then heat from the sun might not penetrate deeply enough to drive water sublimation until later in the approach. Thus, CO2 and CO, which require less heat or can sublimate from shallower depths, can dominate the coma much earlier. The observed CO2-dominated coma supports that scenario. The concept that such an object carries an insulated ancient shell through which the sun's heat must slowly beat down opens up a view of cometary behavior that is more complex than we ever assigned to solar system comets. This then touches on planetary science and the study of planetesimal formation in different star systems. If 3.I/ATLAS's original formation environment placed it beyond the CO2 ice line, or at a distance where CO2 ice was abundant, the current composition might partly reflect that. But because of the heavy processing, disentangling the initial conditions from the evolutionary overprinting becomes much harder. Scientists note that an intrinsically CO2-rich nucleus may indicate formation far from the parent star, or near the CO2 ice line in the protoplanetary disk. But now, they also argue that far more of the current coma composition is shaped by cosmic ray processing rather than formation chemistry. The balance between those two influences is now a frontier. Another line of implication is the age of the object. 3I/ATLAS may be significantly older than our solar system, possibly on the order of 7 billion years or more. If that's the case, then the journey it has undertaken, its exposure to the galactic environment, has been dramatic. It opens the possibility that objects traveling between star systems for billions of years will systematically evolve towards certain chemical and structural states, ones that might converge despite widely different formation conditions. In other words, an interstellar comet discovered today might carry the imprint not just of its birth system, but of a galactic aging process that modifies it in a predictable way. For observers and modelers, this invites caution. A composition measurement alone may not immediately reveal the birthplace conditions of the object. Instead, it might largely reflect the cumulative exposure to galactic cosmic rays and interstellar processes. In practical terms, for future interstellar object discoveries, scientists will now have to ask, how long has this object been roaming? What has it seen? How much of what we detect is original, and how much is processed? The JWST data on 3.I/A TLAS forces this reframing. From a dynamics point of view, its hyperbolic trajectory confirms its interstellar origin. But now the interior story of its constituent materials is more complex. Its activity, outgassing, tail formation, and coma structure must be interpreted with a dual lens: formation plus exposure.